Limiting reactant. In this video, we're going to focus on when we have more than one reactant and we know how much of each reactant we have, how can we figure out which chemical is going to run out first, or which chemical is the limiting reactant. This can be tricky because could be a different ratio of consumption for the different reactants, but also because we measure the reactant's mass, and of course mass doesn't necessarily tell us the number of particles, so because some particles weigh more and some particles weigh less, we have to take that into account first. So here's our little cookie analogy. Imagine you're making some sort of recipe that has 2 eggs for every 1 cup of flour. There's your cup of flour, there's your 2 eggs. And when we're really doing anything with cooking, we'd be able to count our eggs, like, oh, we have 1, 2, 3, 4, 8, 12, whatever eggs. And our flour, probably what we would do is we just scoop it and see if we ran out. But what if instead we had to figure out how much we could make, but all we could see or all we could measure was the mass of the eggs or the mass of the flour? So let's just, for the sake of this analogy, assume that we had 100 grams of eggs and 250 grams of flour. Well, you might look at that and say, oh, those eggs are going to run out first. But remember that eggs don't necessarily weigh the same amount as a cup of flour. So let's look at this more carefully. If I have 100 grams of eggs, and I want to get that into a number of eggs, what I need to know is the mass of a single egg. Here I have 25 grams as the mass of a single egg. So what that tells me is I actually have 4 eggs. Similarly, if I have 250 grams of flour, if I want to know how many cups I have, I need to know the mass of an individual cup of flour. Now here I've written it's 100 grams. That's not accurate. I'm just making up numbers to make the numbers work out the way that I want them to. But for the sake of this discussion, for the size of cup we have, 1 cup of flour is 100 grams. So if I have 250 grams total, and each cup weighs 100 grams, that means I have enough to have 2.5 cups of flour. Just going to label these eggs and cups of flour. So you look at that and you might think, well, look, I only have 2.5 of those and I have 4 of those, so shouldn't this one run out first? But our recipe calls for 2 eggs for every 1 cup of flour. So we have to take that into account too. So if I had 4 eggs, that means I could make 2 times the recipe. 4 divided by 2, it means I could fulfill the recipe twice. If I have 2.5 cups of flour and I divide out by 1, then that means I could make 2.5 times the recipe with the amount of flour I have. So now that we've taken into account the mass of the individual atom and the ratio in which the atom is used, now we can compare these two numbers and see that the eggs can only make 2 batches or 2 times the recipe, and so the eggs will run out first because the flour can make 2.5. Some teachers would do it that way. Other teachers would ask you at this point to predict the limiting reagent and then use that to predict amount for other reactant. And then compare to amount available. So for example, if I was just looking at these and I guessed that I had 4 eggs was going to be my limiting reactant, I can go ahead and predict how much flour that would react with. I want to convert from eggs to flour. So for every 2 eggs, I have 1 flour. So that would mean I need 2 flours. And here I can see I have available is 2.5. So I only need 2. And so since when those 4 eggs were gone, there would still be 0.5 flour available, we can say that the eggs run out before the flour. The thing that runs out first is called the limiting reagent. The thing that's left over when the reaction finishes, like the flour in this case, is sometimes called the excess reagent. And the excess reagent is what's the reactant that's left over when the reaction is complete. So that's my analogy to cooking. We have to take into account the mass of an individual and the ratio in which they're used, whether we do it this way or this way. Let's do this with real chemicals. Methane is combusted with oxygen gas, and the question is it going to be complete combustion? Remember, complete combustion occurs as long as oxygen is not the limiting reagent. Oop. So first of all, to do this, we better balance this chemical equation. So I need 2 hydrogens, and that means I need 4 oxygens. So I need 4 oxygens. Carbon is balanced. Okay, now that I have this reaction balanced, I know I have 5 grams of methane and 12 grams of oxygen. The first thing first, I have to take into account the mass of the individual molecule so that I can get these over to moles. So if you prefer that equation, you can do that, or if you want to convert. For methane, I have a molar mass of 12 plus 4 times 1, or 16 grams per mole. So for every 1 mole, there's 16 grams. So 5 divided by 16 gives me 0.3125 moles. For oxygen, my molar mass, this is for CH4, for oxygen is 2 times 16, which is 32. 32 grams, and every 12 divided by 32 is 0.375. Now, if I forgot about my mole ratio, I might look at this and say, oh good, complete combustion. That means I'm not making any carbon monoxide or soot. But if I take into account my mole ratio, I think it becomes fairly obvious that actually the oxygen is going to run out first. If I want to just do that by dividing by those coefficients, I can see that since 2 oxygens get used in every mole of reaction, the oxygen is only going to be able to do 0.1875 moles of reaction, where the methane is going to be able to do this much. So obviously, that's a 1. It's important. This is the limiting reagent. If I wanted to do it the other way around, if I suspected that let's just say I suspected wrong, my methane was my limiting reactant. 3.1 or 0.3125 moles per liter. Where am I getting? 0.3125 moles of methane, and I want to convert from methane to oxygen to figure out how many moles of oxygen that's going to react with. So I'm basically multiplying by 2 here. And I can see that that's going to want to react with 0.625 moles of oxygen. But I only have 0.375. So obviously the oxygen cannot meet the demand of CH4, which means oxygen runs out first, which is incomplete combustion. So that's how I figured out what the limiting reagent in that reaction was, taking into account the mass of an individual particle and the ratio at which those particles are used.